what we're gonna do today is to use the dynamic push relabel again to get to expanded decomposition, with respect to degree node weighting, but without any black box in this time, nonlinear time, with when phi is like not too small. Okay, and let me like kind of recap what have we done. Okay, so like on Thursday last time, we were saying that okay, so this is our goal today. First of all, to get expanded decomposition and even the boundary linked version. Okay, when the node weighting is degree in this time. This is a goal today. And expanded decomposition, if you recall, like our algorithm, okay, there are really just two subroutines that you need. Okay, one is the way to get balanced sparse cut, like subroutine that either return you a balanced sparse cut so that you can just recurse on both sides, or the one that will return you a giant expanding set where you don't need to recurse and just you need to recurse on only one small side. That's the subroutine. Okay, and so we saw on like last Thursday that to get this one is enough. Like we see how to solve this using block max flow, but it's actually enough to solve some routine called cut mesh, which I will recall today what it is again. Okay, but we say on last Thursday that if we have this subroutine called cut mesh, which I will recall, then you get this one. Okay, and fast. Okay. So that's from last Thursday. And on last Friday, we also see how to get expanded trimming, which is basically to trim the giant expanding set. Yeah. And once you have this two, then you get this one immediately. So to get expanded decomposition for today, it's really just enough to solve this one. That's the goal today. Okay. All right. So I will recall what this is. And once we see how to solve this one, you can go back and recall how it gives this one, and recall from Friday how to get this, and it just gives you this one. Okay. So this will give you expanded decomposition for degree node weighting. Okay. And what's nice about this is that once you have expanded decomposition, you can actually get three-flow specifier. Okay. Even when the node weighting is 4 degree only. Anyone recall how? From here to here. What's the algorithm? Yeah.
Like a hierarchy from the expanded decomposition, and then you just build a tree from the hierarchy.
How do you build a hierarchy from the expanded decomposition?
You just call it on each like component.
Say again?
You just call like decompose on each component and recurse.
It's not quite that. It's more bottom up. How would you? Do you recall? Like what you said, Michael, is that you find expanded decomposition with, which is like it kind of decompose the graph into pieces, and you said that you recurse on each of these pieces, right?
Oh, it's actually not. Yeah, you do it on like the cut.
So what you do from here to here is to contract and recurse. Okay. So you get the expanded decomposition, you contract each piece, and you get smaller graph and recurse on the smaller graph, and contract again and contract again. That gives you the tree structure. That tree structure will give you this one. Okay. So I will not, like if you want to record, you look at this lecture again. Okay. Just, this is like kind of a fast way to build tree flow specifier. But you need the bodily link version here. Okay. But anyway, this is today's goal. And let me recall what is cut match algorithm again, problem again. Okay. So the cut match problem is this. It's a problem where you either find a sparse cut or you match the two sides, but you match. The flow should match like between A and B outside the cut. So what I mean here is this. You have a graph, see? You have A and set B. Okay. And think of A as not too big, like 1/8 fraction on at most. B is like at least half. And what we would do is we're gonna return both a cut and a flow that match two sides. Like we want to return both, not just one. And what we're gonna do is we're gonna return a cut, maybe a cut S like this. Maybe cut S, yeah. And this cut should be sparse with respect to degree. The cut S is sparse. And it shouldn't be too big. Like here I relax a bit. Like instead of saying that the volume of S is at most half, I'm okay with like having it a bit more than half, but the other side still need to be quite big because it's at most 3/4. Other side is at most, the other side is at least 1/4. So it's not too big, yeah, and it's fast. But in the general case that you should think of as is actually like maybe it's tiny actually. Yeah. Okay. And then we also return a flow. Okay, a flow. A flow should basically match between everything on A outside S to B outside S. Everything from A is saturated. And they should go, like it shouldn't go here. Okay? I want to respect B minus S. So it should just go to B, to B minus S. Yeah. It cannot go to B intersect S. Okay. So this is what I mean by it only match source and sink outside S. Okay. Everyone outside A, outside S on the A side is matched. And it only matched to the guy outside the cut, not here. So, okay. I mentioned in like on last Thursday that if you actually gonna match to the guy inside the cut, then it will not work with a cut matching game. Okay. So we need to match to this guy, to outside S. All right. Is the problem clear? Question about the problem? Yeah.
Is it clear that these will exist, I guess, at F and S?
Yes, because if you just compute max flow and min cut, you're gonna get like you can say that S here is your min cut, and the flow after the cut will indeed like only match outside the cut. So what I mean is like suppose that S is just a min cut, right? then if you look at the max flow after the cut, it will look like everything outside the cut, like everything here will match to some guys here, and everyone here too, actually will match to some guy here. So there is no way that the flow from, let's say, node U, it will not go like, it cannot go like this to here. Why? Because you know that the flow along the cut kind of go in this direction. So you cannot actually, send flow that reverse the direction of the cut. Yeah. So you know that like you will not match to this guy. So that's like, if you just use max flow min cut, you get this immediately.
It's like the structure of max flow min cut that you.
Exactly. Exactly. Yeah. Okay. More questions? Good question. Yeah.
What happens if S is like big?
What happens is if S is big?
Yeah.
So when you know that A is not too big, you know that S is not going to be too big.
Oh.
Because the intuition is that like there is just this much source that you want to send, and like, how to say this?
Is it because like D is more than half?
Yeah, B is more than half, but A is like A is so okay. Good. Maybe think like this. Imagine that you really just do max flow min cut. This is A, this is B. Okay. If actually S looks like so, if S looks like this, okay, you know that like the flow before the cut will saturate all the sink, and actually saturate the guys on the cut too. Okay. So everyone on B need to be saturated. But B, if S is so big, so there are so much sink that is saturated here. But the total source is small. So that cannot happen. Make sense? Yeah. Okay. More questions? Okay. So yeah, it's actually a good exercise to just convince yourself that, okay, if you just use max flow min cut, you just can, this just solved. Okay? But here we're gonna find a way to not use that black box. Okay. And we will solve it in this time. And the algorithm is gonna be dynamic push relabel like on last Friday. It's just gonna be so similar actually. Yeah. So let me record the notation again. So like there will be a notion of alive set, right? Which only shrink. So the algorithm, how it will go is like, it will like, you start with the graph G and we will kind of keep finding some cut and kill something, finding another cut and kill it. So this is the alive set. Here kind of keep shrinking. This is alive. Just like last time. And we will have like the graph and the flow and level and the source function, sink function. We will kind of only keep working on alive part, just like last time. So whenever this alive set shrink, we just kind of restrict ourselves to alive set. The flow is restricted to alive set, and everything just restricted to alive set. Okay. And okay. And also again, like we use push relabel, which maintains some label on vertices. So Li is all vertices with level I, and this is just denotes similarly. And G consecutive is just a graph consists of only when you fix the label, it contains only edges that connect between consecutive levels. Okay. So all this is just like last time. Now, the algorithm for cut mesh is like this. We start with usual stuff, which is empty label, like zero label, empty flow, and the source, the sink is just what we said. Like this is the goal, right? The goal is to send flow from like kind of A like scale, like the degree not weighting on A scale down by 5/8 to degree not weighting on B scale down by 5/8. So the sink should just look like, the sink just look like degree not weighting restricted to B scale down by 5/8. This is just the sink. And we set the height to be this much. Okay. If you remember, like when you set the height to be this much, it's long enough. It's still quite short, but it's kind of long enough so that when you look at like levels, there's gonna be like a 5 sparse cut in what graph? In Gcon. Okay. Like when you look at the graph that only have consecutive edge, like edge in the consecutive level, there's gonna be 5 sparse cut in this graph Gcon. Okay. So it's okay. And then we just use like a tight edge data structure like usual so that we can do push the label. Okay. And the alive set in the beginning is just everything. Then the source is just what we want to send from A. Just from A scaled down by this much. All right. So now, okay. So now what we do is just this. We have the graph, we have A, we have B. Okay. Then we just keep trying to push and relabel the active node until every node, like every node with access is dead. Every node with access at level H. So just try to keep pushing flow from the source here. Okay. And okay, if there is no access, we are done, right? It just means that, okay, here there is even no cut. We really just send all the flow from A. Everything from the source here is successfully sent to B. And the cut is just empty. So we're just good, like easy, this case. So far, this is kind of like last, like what we discussed on last Thursday. Okay. But on last Thursday, from last Thursday, if actually there is excess left, we didn't succeed in sending out the source, then we know that we can find a sparse cut in Gcon. Like, we can look at Gcon and look at like the level graph, L0 up to LH, and we know that there exists a cut, like exists some cut of level at least I, right? Such that this cut is sparse in G-con. So this cut is smaller than the degree in G-con of this cut, of this set, like 5 sparse. And I can choose this thing to be any constant. In this lecture, I choose it to be quite small. In previous class, we choose it to be like 4 or something. Okay. So this will like, as long as h is like is this, h is like a log n over 5, order of log n over 5, this can be like 1,000 or anything. Okay. So this is like a sparse cut in G-con. And again, it might not be a sparse cut in G, right? Because G-con is just a subgraph of G. There can be like a lot of other edges crossing in G. Like that is not, that's kind of skip levels. But can you recall what's the key property of the edges that skip levels? It has something to do with flow. What's the key property of the edge on that skip level? How like can the flow on this edge be like not saturated? So I claim that every edge on the graph, on every edge that skip levels must have saturated flow. Do you see why? Okay. So, I mean, if there is this edge that skip level, but let's say the flow is not saturated, okay? So let's say the capacity is 5, but the flow is 3. Then what will happen to U and V in the residual graph? It means that in residual graph there is this like there's still like a NH from U to V with capacity 2. Are you with me?
Was that edge stretched or did it
Yeah.
stretched right?
Right.
Okay.
Yeah. So now, yeah, this edge is the edge that go downhill from U to V. But now the level of U kind of is more than V by 2, at least 2, because it's skip levels. So now it's just overstretched. That cannot happen, right? So if you don't want any overstretched edge, it means that the only choice is to saturate this one so that this edge doesn't exist in GF, in residual graph. So that like only this edge exists. Okay. So this is the thing to keep in mind. There is no overstretched edge in residual graph. Okay. Okay. Anyway, this is just to recall the thing from last time. Like the edge that basically skip levels, they are saturated. Okay. And from last time, we just said that, okay, what we're just going to do is just, we find this cut is sparse in Gcon, and we just return this cut and claim that it's sparse in G. Okay. And this is going to be the case. It's going to be true. Okay. And the reason that it needs to be sparse in G is just because the green edges that skip level, I claim that there cannot be too many too, because they like all the flow saturate them, but there are not too many, like the flow that can go out of this is not too much. It means that the green thing, the saturated edge, need to be not too many too. So that's why it's sparse. So that if all we want is just to get some sparse cut, that's okay. We just return this and we are done. But it's not enough for today, because when we find some sparse cut, we want that, again, like there is no flow from the A guy outside S that actually go to mesh to B guy inside S. We don't want this, right? In particular, what I want actually is like every edge crossing the, if I want to prevent this, what happened in MacFlow is that every edge along the cut is actually have some flow saturated in this correct direction. That would prevent this bad event from happening. And we're going to do this, actually. We're going to try to make this happen. But right now, if we just return this cut as your sparse cut, it's sparse, but something might go inside. Like some flow might be sent in the reverse direction. We don't want that. Okay. So what we're going to do is just this. I'm just going to say that I find this sparse cut. I kill it. I kill the sparse cut and say that the remaining alive part is just L less than I. Just like last time. Just kill the sparse cut. And then continue. Continue how? The source. Okay. This is just natural. Like the source now we just try to send from A, from the alive part of A, because the part that is not alive is killed, is kind of removed from the graph. Okay. But also we're gonna try this too. Try to send from the battery. Okay. So, for example, look at this picture. Suppose that I have A here and B here in the beginning, right? Maybe I have cut something, and then basically all edges that cross the cut, basically I try to send flow in the correct direction from the cut. Basically this thing is just to inject flow in along the cut here. Okay. When I cut, I set the source to be like this, and then I just repeat here. I remove some part of the graph and repeat calling push label again. Right? When I remove some part of the graph here, now like not like the node that like the excess on the level H is now removed. So like not like now I can continue my algorithm on this part, right? Just keep pushing until all the excess are dead again. Like keep pushing and relabel until all the excess has increasing its level to level H. And once this happens again, I just check if I succeed or not. And if not, I just cut and kill. Okay. Just continue like this. So if I kill again, then I kill this thing. I might fire a cut and kill again. Okay. And when I kill, then the edges crossing this cut like will induce some new source, like which is just basically encode here. Okay. So this part is just to encode like the remaining original source, and this part is just basically to enforce that I now don't want to just send flow from the source A. Every cut edges that I made so far, the red edges here, the red edges, I want to send flow in the correct direction. I want to make it such that I can send this flow, just like what happened in MacFlow when we compute MacFlow. So in practice, it means that like, suppose that I have cut this guy and this guy, then if you look at the new source at U, it would look like degree of U, scale it down. It's not U, but now you're gonna have this capacity of an edge E1 here and capacity of edge E2 here, right? Because basically I want to inject flow from the red edges, from the cut edges. So that's the algorithm. So when you cut, think like you inject new flow along the cut edges. For every cut edges, you just inject new flow equal to the capacity of each edge. And then continue. Continue again, like try to push flow after that. And suppose that I succeed. Suppose that after making this cut, then I succeed. Then what it means? It just means that everyone in A, I can match to some guys in B. But actually, it's like every edge here, I can match to some guy in B too. Right? Every cut edge, I can match to some guy in B. Okay. So this is just like what happened when you just use MacFlow. So basically whenever like I do this thing and I redo again and then the next round there is suppose that in the next round there is no excess. Then basically we succeed in sending this flow, this source to the sink. Are we good? Is the algorithm like description clear? Okay. Good. So from here I hope you can see that from here it means that after termination, indeed we'll saturate everything in A minus S. Like, so again, when we return, when we succeed, then when we succeed, there is no excess left. S is just everything that you have queued so far. Okay? So for example, like this would be S. Okay? And F is just the flow on the alive part. Okay? So when you terminate when there is no excess left. So you know that F just clearly saturates this guy because it even saturates this thing plus, degree on the boundary of a live set. So it saturates even more. So it would saturate this part. Okay. But also, F will respect. It will send to only sink outside S. Because now we know that the flow cannot cross the cut in the wrong direction. Right? I claim that all the flow here just go to some guy outside S, the sink outside S. Because just like we have seen, every edge along the cut of the cut S, you send flow in the correct direction. So there's no way that actually I send flow from this guy crossing S in the wrong direction to match some guy in S. Right? To match from A outside S to B inside S, I need to cross S in the wrong direction. And that's not gonna happen. That is like, we guarantee that doesn't happen. Okay, so it means that once we terminate, we are just done. We like, this is true. Like matching source and sink outside S is guarantee. Okay. Question about this? Okay. So what's left for us to do?
We need to prove S is, did we prove S is a small?
Yeah, we need to prove that S is a sparse cut. F is like a phi sparse. Okay. So like the guarantee about the flow, when we terminate, we are done. Just now, like we need to guarantee something about cuts. Okay. Questions? Okay. All right. Okay. Also the running time and why actually the invariance is maintained. The running time is going to be like this running time, which is like h is log n over phi. So this is like just m log square over phi. And also we can see that the invariant required by push Relabel is maintained, which is that there's no edge, no overstretched edge in the residual graph, and F is always a preflow. This is going to be maintained. I will ask you to like recall this proof is just the same basically like last class on Friday. Okay, so this is, I'm just going to skip this. Okay. Basically, it's just the same proof, but for sanity check, right? For this exercise, I'm just gonna ask you one thing. Okay. So suppose that when I Q some set, okay, then I set the source function to be this part, which is the natural part. Like just the remaining source, the remaining original source. But what if I say that I add this much source? Like instead of 1, yeah, this is like a less than 1. What would go wrong? Like which, either this running time or this one or this one, which one should go wrong? It might not be so easy actually, but yeah. What do you think? Yeah.
I'm not really too sure, but is it something with the pre-flow? Like we're not running out of flow, but like we're losing something along the way, so we won't be able to, I guess, continue it.
Yeah. So you said that like pre-flow is wrong. What about others? Before I answer. What do you think, Kiran? Which one is wrong?
I think it's the relaxed condition because
Relax. Okay.
it,
Mhm.
I mean, I'm not too sure, but we've always studied the overstretching condition and the degree weighting. So if you go with half, I'm not sure how exactly.
Okay. How about others?
I'll just guess pre-flow.
Okay. David.
I was thinking also relax because changing that degree might cause some overstretches and stuff like that.
Okay.
Maybe pre-flow.
Free flow. Okay. Yeah. And the correct answers go to free flow. Okay. So let's see why. Okay. The reason is this. Like what it means to be pre-flow, first of all, just to recall, it means that the net flow out of each node is at most the source that you have. You don't send more than you have in total. That's okay. You might receive more than you have and don't succeed in sending it to the sink. That's what it means to be pre-flow. You don't succeed to send to the sink, but you don't want to send more than you have. Okay? You don't want to have deficit. You can have excess. Okay? That's what it means to be pre-flow. But so now let's look at this like scenario. Just imagine that maybe like there are some flow paths that just go through you. And let's say that you don't even have like original source. Originally you have like zero source. And there's just some flow path going through you like this. Like 10 unit of flow. Okay. And when I queue, suppose that I queue this cut, right? Then previously, before I queue, the net flow out of you is just zero because it's just flow going through you. But now the net flow out of you, when this thing disappears, then the net flow is now like 10. Because now this disappears, looks like you just send 10 units of flow out of itself. Okay. But to make sure that this is a pre-flow, it means that we need to say that now the source at U, after I queue this, should be at least 10 too. Right? That's what it means to be pre-flow. The source at U need to be at least flow out. Okay. So in this case, I need to set like source at U to be at least 10. But in general, actually, like how much flow out of U can be increased? It can be increased as much as the boundary. Like actually, in general, this thing could be replaced by the degree node weighting of the alive part, right? At U. Everything here could have sent to you. The amount of flow that's sent to you could be as big as this. So we kind of need to set the source to be as big as this thing to make it a free flow. Otherwise, if it's less than that, then it looks like you just send flow out of nowhere. Okay. So that's kind of explain why you set the source function to be just this thing. Okay. This is basically needed to make sure that you always have a preflow. Okay, good. So is it clear? Like this is, you see this, right? This would go wrong because you want preflow. And yeah, try to look up from last class. It's the same proof. And try to convince yourself to understand what happened today. Prove this yourself. Okay. Okay. Yeah. Okay. So now let's say that let's prove that S is a sparse cut. Okay. So like the running time is like last time. Why the algorithm is valid? I just basically kind of give you the main idea here that it's valid by the same argument like last time. But what's kind of important is that we make sure that it's always a preflow and we never overstretch. Okay. And if we terminate, then the flow is as we want. What remains now is just to prove that the cut is sparse. Okay. So let's prove that the cut is sparse. And the key idea is like, okay, similar to last time, let like a initial source to be just the initial source function, which in our case is this thing, intersect A. Now let this thing, like the total increase of the source, to be the total unit of mass that we kind of additionally add into the system. But we don't count the initial mass. So when would this increase? It's basically just when we cut and we inject flow along the cut edges. This is like every time that we inject flow along cut edges, every time that we inject additional flow along the cut edges, that's when this thing increases. Okay. And this total here is just the initial total amount of mass and the total increase. Okay. But we focus on this one today. So just like similar to last time, when I have this node, these two edges, and when I kill this guy, right, then we would try to inject flow along this edge to be like full capacity. If it's already 3, then we need to inject 2 more. And for this one, if the flow go in the wrong direction, we just need to even inject like 6, because we want to inject flow in this direction at full capacity. So we need to cancel 1 and inject 5. So this would increase by 6, like last time here. Okay. And now I claim that the total increase, here is not too big. How big is something like degree of S times phi. Okay. So we're gonna prove this last. Suppose for now that the total increase is small. Okay. It's something like phi times volume of S. Suppose that's the case. Let's see why we are done. Okay. So first, if you have, I can from now assume that the total increase is something like phi, like tiny thing times degree S. Okay. Now let's prove that the size of S is small. Like the cut size is small. This is basically almost like to say that S is sparse. Except that I just proved one, like if I need to prove that it's sparse, I need to prove like this phi times min of this thing and like V minus S. I just proved one side for now. Okay, so let's get an intuition first why it should be sparse. Okay, S is here. Okay. What we know at the end is that every edge that go out of S is basically saturated, because we kind of we said that like we saturate flow, like the source that like we saturate this thing, right? We saturate this battery source. Basically, you can think like we successfully send like every edge crossing S kind of send flow to outside S. All these edges are saturated. So it means that F out, the flow out of S, is really like the cut size. Okay, we have this. And now if we want to upper bound this one, just need to upper bound flow out of S. Okay. How big can this be? Well, first, the flow out of S is at most initial source of S. Like you cannot, there are some source originate from S, it might go out. Are we done here? Is this true? Like, is there something else? Like if I just write like this, is it false or is it true? It's not enough yet. Why? Like this could be false. Why is that? So basically, it's just because we inject more flow, right? Like, if we never inject any more flow, this would be true. But every time we cut something, we actually inject some more unit of mass into it. So, like, you might need to, like, there might be like this unit of mass that kind of goes, like when you might have cut something inside S here, right? And we actually inject something new here in every time that we cut. Yeah.
But that statement's true in the original, the first cut though, right? Before we add anything else. Like it.
Say again.
This only happens after we add more and more cuts.
Yeah.
The first cut, that would be true, would have been true.
The first cut that this would be true.
Yeah.
Exactly. Yeah, but S is really like union of all the cuts that we have found so far. Yeah, good. Yeah. So if S is just the first cut, this is true. But now, yeah, this is a kind of many cuts that we have found so far, and all the previous cut that we have found, we actually inject something more, some more mass inside it. So this additional mass might be inside here, and it can go out of it. So that's why we need to bound F out by initial mass inside S and the total mass, like the total increase. Actually, this can be said that the total increase inside S, but I just be relaxed here. Okay. But now we are kind of done because the total mass inside, initial mass inside S is just like this thing by definition. And the total increase is just what we claim. I claim this. So summing this together, it means that the cut size is at most like this thing plus this thing is certainly less than 5/4. So this is good. So, but now I kind of need to prove, what I want is to prove that like this thing is actually less than 5 degree S and degree V minus S. I need both sides. So how do I prove this? Like right now I just get one side. How do I prove this? I just gonna say that like this cannot be too small. Okay. So I claim that this side is not too small. So why is that? Well, the idea is this. The idea here is going to be similar to what I explained to Michael from the beginning. Basically, I have A and have B. Okay. And if this is S, we're going to have that everything here is saturated. This sink, the sink capacity in S is saturated. This is saturated. Okay. So it means that okay. First of all, do you see that like the sink capacity of everything in S must be saturated? Do you see this? Like because right when we cut something, we find a level cut of level at least I. We never cut something on the level 0. This guy are unsaturated sink. The sink here are already saturated. So all the sink that we have cut, they are always saturated. Okay. So everything that we cut, if they are sink, this part is saturated. So it means that there are some mass that kind of come from the source that come to saturated here. So if this part is so big, like first of all, we're gonna say that like the total mass that we have, like A in the beginning is small. The total mass that we add into the system is not too big. So if both of these are small, the total mass is small, then this part cannot be too big. Because they are like these are saturated by some mass in the system. And if this is not too big, it means that this remains big. This is huge in the beginning, and this part is small. So it means that the other side of S should be still big. That's the intuition of everything. Okay. So let's prove this formally. So we have that the total sink in S can be bounded by some mass, the total mass in the system, right? Because they are saturated. What's the initial mass in the beginning? It's just degree of A scaled down by 5/8. This is just the thing in the beginning. The thing that we add in addition is just this one. Okay. I just use a kind of easy bound to, okay. Let's say, maybe I do it like this. Okay. So, okay. So like the idea is that this thing is small. Okay. Like think of this thing as small. And now we're gonna say that okay, this if this is small, this should be big. Okay. Because this is what is the thing here? It's just this thing degree of S intersect B, right? So this part is small, so this part should be big. So what I do formally here is just I write down degree of V minus S, so this part. Okay. This part is just the sink and then scale up by 8/5. The sink at V minus S is the total sink minus the sink at V, the sink at S. Okay. So now, okay. Maybe this is not too clear. I just gonna maybe write it. Maybe I just write it like this. This thing is at most, right? Maybe I just write it like this. Degree of S is at most degree of A plus 1/8 S. Here, maybe forget about this thing. I really just like scaled everything up by 8/5 to get to this, right? But this one, A is like at most degree G over 8. This is just from the from our assumption that A is not too big in the beginning, and this thing is just clearly at most degree of G over 8 because degree of S is at most the total degree. Okay. So now this is at most degree G over 4. Okay. But we know that degree of B in the beginning is at least degree over 2. That's the assumption that B is big. So if this part is at most 1/4, this part is at most 1/4, but this whole part is at most 1/2. It means that the remaining part here is at most 1/4, at least 1/4. Okay. So even this part only is at least 1/4 of the whole thing. So it means that this whole thing is at least 1/4. Okay, good. Okay. So you see that, yeah, like, so now both of these bounds use the fact that the total, like, increase in the mass is not too big. So now we just need to bound this thing. That's the key part. Like, that's the only remaining part now. Like, oh, sorry. Once you have that, the cut is small here, and the other side is not to like remain quite big, then you basically get that, you get this thing now, right? Because like how do you write this? Well, like this thing is just we show this one. We show this one. Okay, but now I want to show this as is at most phi of this thing. Okay, so why is that? Well, like I mean, because if I show both of this, then we are done, right? But why is that? Well, this is at most clearly phi 4 degree of everything, but this is at most phi degree of v minus s, because v minus s is not too small compared to everything. Yeah, that's it. So we are now done, basically, except that we need to prove total increase. Okay, so let's prove it. Okay. So the idea is similar, like we're gonna increase some flow every time we queue some cut at like of level, some level cut of level at least I. So let's analyze like every time that we queue a cut, how much we increase. Okay. And suppose in the simple case again that like when you cut, when you fire a cut, if all the flow are saturated, like the cut edges crossing this thing, they are all already saturated. Like the flow out of this is just the cut size. All edges crossing this thing are saturated from direction from here to here. Okay. Then I hope you see again that this wouldn't increase at all, right? Like you see, like here for this edge, if the flow is not saturated, then we increase by 2. But if this is just saturated in the correct direction, we wouldn't increase. We didn't need to inject more mass into the system. So all the saturated edge, we don't need to pay. We don't need to add more mass in the system for each of these things. Okay. So how much? How much of the how many edges might not be saturated? We know that all the edges that skip level, those edges that are saturated, right? So that one you don't need to count. You only need, so now you just look at edges that don't skip level. Those edges might not be saturated. So basically, the guy that don't skip level, they are basically from Gcon, right? The edges that don't skip level, they are from Gcon. This thing is the total capacity of edges that cross the cut and don't skip levels. And they might not be saturated, and they might be sending flow in the wrong direction. So the total mass that you need to like you might need to like add into the system is basically twice of this. Like twice of this. And how big is this thing? Can we bow this one? What's our choice of the cut here? Like the choice of our cut, that we just literally just choose the one which is what?
Of the sparse.
It's sparse in Gcon.
Yeah.
Yeah. So that's why this thing is small. It's something that we can control, basically. Right? Every other edges that like skip level, there can be many, but they are all saturated. The edges that don't skip level, we might need to inject more flow. These are the dangerous one. But we literally just choose, like for Gcon, the push level allows you to to create many levels and just choose the one such that in Gcon it is sparse. It's small. So this one is small. Like it can be like a phi over anything of the volume of this cut. This is small. Okay. So in general, this thing may increase by at most twice of the capacity of edges crossing the cut in Gcon, we choose it to be small. Can you tell me why can we conclude this now? So every time that we cut something, we increase it by this much. Why in total, we're gonna increase it by this much?
It just takes a union also.
Exactly. It's really just a union, right? We cut this guy, we increase it by 5 times its volume. Then we continue the algorithm. We're gonna cut maybe again. And we increase it by 5 times this volume, this joint volume. And do it again, cut it again, and increase it by 5 times this volume. But then it means that in total, S is literally just the union of this guy. And so every time that we, the total increase is just 5 times the total volume here. So that's why we get this one. Make sense? So we are done. Right. Okay, so basically, what's the message here? The message is that in both expanded trimming and in this case today, we basically, what we want is to get some cut such that edges crossing the cut have flow that every single edges crossing the cut, there are flow that saturate them in the correct direction. Okay. And okay, in the beginning, this is something that is satisfied by max flow. When we don't have max flow, we don't have this, automatically, but we can try to make it true. How? Basically, when we fire a sparse cut using push level, we have a lot of skip edges that skip level. This guy are the one that already saturated. But there can be some guy that is not don't skip level. This guy are the one that is not saturated, unset, but small, right? Because when you do push Relabel, this thing is like the guy in Gcon. In Gcon, this thing, you can control it to be as small as you want, like 5 times the volume of this guy. So this thing is small. So okay, there are some small things that you kind of need to fix. What we do, we just try to fix it by saying that, okay, this is not saturated yet. Try to inject flow here, and then continue your algorithm. And you try to inject flow here. And okay, if it turns out you succeed, you're good. If you don't succeed, it means that, again, the algorithm will return some cut. And most of the edges here will be saturated again. And there are going to be some edges that are not saturated. And this thing is small. So okay, try to inject flow again along this thing. And keep trying to do this. And you say that like the key point is that you want to say that you don't, like, in total you don't inject too many. Okay. And but when we succeed, we just get the union of the cut such that edges crossing the cut send flow in the right direction. Okay. So this is what happened here. In expanded trimming, we really just want that too. Like we start with u prime, like we start with u, right? And we kind of want like u prime such that every edges crossing u prime have flow in the right direction. Okay. And the idea that we can cut something and just continue the algorithm without restarting the whole algorithm again. This works because push Relabel really just maintain this cut edges data structure. When we cut something, it just removes edges, no new overstretched edge. So we can really just continue our algorithm. Okay. Questions? All right. So what we have now is we get this one. We get cut mesh. And so we get this one from Thursday. We have this one from Friday. And recall, I hope you go to recall that like we can get this one. And from here, we get this one. From next class, just going to assume that we can build a 3-flow specifier by ourselves. And we're going to see how to compute approximate max flow. Approximate flow in undirected graph. Okay, in this time, without any black box. Okay. So I'm just going to assume this to get this. Okay. So previously, we saw some push Relabel algorithm that give you approximate max flow in some directed graph, but like maybe like bounded depth graph, like matching, like bipartite matching or low depth graph. Here it's just going to be fast no matter what, but only in undirected graph. Okay. So that's like a breakthrough like 10 years ago. And we're going to see it next class on Thursday. Right, see you. Yeah.